So Jai Hind everyone. Today we are going to this lecture in continuation with the previous lecture, that is the junction field effect transistor. We have already discussed between the difference in the previous lecture. We have already discussed between the difference between the bipolar junction transistor and the field effect transistor. BJT is a current control device, FET is a voltage control device, BJT is a bipolar device, and FET is a unipolar device. Input impedance of the BJT is low, output impedance of the BJT is high. The temperature sensitive BJT is more temperature sensitive in comparison to the FET. Also, the temperatures, apart from the temperature sensitivity, the noise immunity. So noise immunity is high in case of the field effect transistor and it is less in case of BJT, but the gain of the BJT is more in comparison to the field effect transistor. But the size of the BJT is also more as compared to the field effect transistor. So these are the few differences between the BJT and FET. After that, we have already discussed about the various types of the field effect transistor. So there are the two types of the field effect transistor, junction field effect transistor and metal oxide semiconductor field effect transistor. Junction field effect transistor are again of two types, that is the N channel and the P channel, and metal oxide semiconductor field effect transistors are of two types, depletion type MOSFET, which are of two types, N channel and P channel, and E MOSFET, that is the enhancement MOSFET, which is again of two types, that is the N channel and P channel. So we have also discussed about the construction of the junction field effect transistor, where N channel, in this figure we can see that this is the N channel junction field effect transistor, which consists of an N type of the semiconductor material, where two pockets of the P-type material has been diffused from both the side, and because of this, when we insert the P-type of material, then because of the concentration gradient of the P-type material, the charge carrier in the P-type of material and N-type of material, there will be the formation of the depletion layer takes place in both the at both the sides. Now, these P-type of semiconductor materials are internally connected, and one terminal is and a metal is connected to these two terminals, and the gate, the terminal is taking out, that is the gate terminal, and on the top and the bottom of the N type of material, again two metal contacts are there, and where we get the source terminal and the drain terminal. We know that the input impedance of the field effect transistor is high, as well as output impedance of the field effect transistor is high. That means the gate to source terminal is always a reverse bias. Gate to source terminal is reverse bias, and also drain to source terminal is reverse bias. And because of that reason, when we increase, also we know that this material is uniform. This I have already discussed in my previous lecture. You can refer that lecture in order to understand in detail that the charge carriers are moving in the upward direction, and because of that, the current is moving in this direction. And because of this current, the drop at different point will be different. Here you are having the minimum voltage drop, and at this point you are having the maximum voltage drop. And because of the variation in the voltage drop, and which is a reverse voltage, the thickness of the depletion region is more. The thickness of this depletion region is more where the voltage drop is more, and it is less where the voltage drop is less. So basically, it is the thickness of this depletion region takes place in an elephant ear like a structure, which is broader at one side and it is thin at the other side. So this is the coming to the characteristics of the PN junction, characteristics of the N channel junction field effect transistor. So this is the drain characteristics of the PN junction, the drain characteristics of the N channel junction field effect transistor. So I'm redrawing the circuit here. in order to make it easy to understand. So this is my N-channel junction field effect transistor. This is P-type material. This is P-type material. Here this is your drain terminal. Here it is source terminal. This is gate terminal. Now gate is P-type and this should be reverse bias. So this should be connected to the negative potential and this is positive potential. So I am drawing a battery here. This is, let's say, VDD. Also drain to source terminal also reverse bias. That is why it is having high output impedance. So this is N-type material. So that to make it reverse bias, this should be connected to the positive terminal of the battery. And this is also, value is same. So I have written this is also VDD. Now, this VDD positive, negative, and this is positive. So the net voltage will be 0 and that is why this will be at the ground potential. Now, initially, because of this VDD, there is a input voltage between these two terminals will be developed, that is gate to source terminal. That is why we call it as VGS. And here the voltage which is developed between the drain to source terminal is VDS. Now initially we keep the VGS is equal to 0. So now let us see what happened when VGS is equal to 0 and you are only changing the VDS by varying the value of VDD. So as you keep on increasing this, the VDS is also increasing. And this positive terminal of the battery will attract the electrons, the majority charge carrier. They will start moving towards the drain terminal, and we know that current flows opposite to the electrons. So because of that reason, the drain current will start flowing in the circuit from drain to source terminal. Also we know that the gate current is 0 in case of the junction field effect transistor. Why? Because of the very high input impedance. Because of the very high input impedance. Why input impedance is high? Because gate to source terminal is reverse bias. So here the current will start flowing. Now because of this current flows through the network and some voltage drop will takes place across the material, that means, and which is a reverse voltage. So because of that, together with the increase in the current, with the rise in VDS, the current will start increasing. Here you can see as we are increasing the voltage, the current is increasing, but at the same time the depletion region is also increasing. If depletion region is increasing, means the path which is available for the flow of the charge carrier, that is reducing. That means the resistance is increasing. That means as you keep on increasing the VDS, your current is increasing, also the resistance is increasing in the circuit. Now, as soon as you reach the value VDS is equal to VP, this is the designed value of any field effect transistor that is designed by given by the manufacturer. So at this point, as soon as this VDS reaches to this value VP, then this reverse voltage is large enough so the both the depletion layers overlap each other. At that point of time, we say that your channel pinch off, and that is why this voltage is called as the pinch off voltage. And at that point of time, you're left with a very small path between the depletion region. They are almost touching each other but manage to pass a high concentration of the charge carrier. And at that point of time, the current which you achieve is the maximum current or the saturated current, and that is why it is called as IDS, a saturated source to drain current. This is the maximum current which we achieve at the voltage VDS is equal to VP and when your VGS is equal to 0. So at that point of time, we get the saturation level achieved. So this is how it works. Now, because at the currently we are keeping VGS is equal to 0. Now, what will happen if we increase the magnitude of this VGS also? So, if you are now in the next case, if you are taking VGS is equal to, let's say, because this is a reverse voltage, so of course it will be -1 volt. Now, this is a reverse voltage, this is a reverse voltage, and this is also reverse voltage. Because both the voltages are reverse, that means the depletion layer will get increases at a faster rate, and that means the current will be reduced. So, here we can say that your current will get reduced because the number of charge carriers which are passing through the channel gets reduced. Now, further, if you increase this value, minus, let's say it is minus of 2 volts, then again the channel will further get reduced and the voltage and the current will reduce and through the channel. As soon as you apply this VGS is equal to VP. When we apply this value, VGS is equal to VP, at that point of time, your depletion region is large enough that they touch each other, they overlap each other, and at that point of time, your junction field effect transistor gets switched off. That means, so it will get switched off. So there will be no current flowing. At this point of time, there will be no current flowing in the circuit. So this is how it works. So we can say that when VGS is equal to 0, if you sum up this, then we can say that when VGS is equal to 0, we get the saturation level, that is maximum current would be flowing with the highest resistance at that point of time. And when VGS is equal to VP, then device will be switched off. So here, we can see that increasing the resistance takes place because of the narrowing the channel. Why? Because of the reverse biasing of the input and output of the junction gate or the drain of the junction field effect transistor. So this is the situation when pinch off takes place, and this is the time when your VDS will be equal to a VP. So when your VDS increases beyond this VP voltage, then what will happen? Then the level of the ID will remain same, but this thickness will get elongated. It will be something like that. So this is the difference. That is the difference that will take place when you increase the VDS beyond VP. As VGS becomes more negative, the depletion region increases. The more negative VGS, resulting the level of the ID reduces. Eventually, when VGS is equal to VP, that I have already discussed, then ID is equal to 0 volt. Yani when VGS is equal to VP is equal to VGS off, then ID will be equal to 0. And at that point of time, your device will be turned off. So the level of the VGS that results in 0 current is defined as by the value VGS equal to VP, with VP being more negative voltage for the N channel device and positive will be the P channel device. So this must be understand by everyone that when VGS will be negative and when VGS will be positive. So this you need not to mug up. You just need to have the clear understanding that in both the cases, we keep gate to source terminal reverse bias. So in case of N channel, gate is P type. That means to make this gate reverse bias, this VGS should be negative. For P channel, for for P channel, this gate is N type. To make this reverse bias, this should be connected to the positive terminal. And that is what exactly is written here, that this is a positive voltage for P channel JFET or junction field effect transistor. So this is the characteristics which are being, we have already drawn this in the previous slide, but here neatly it is again shown here. Here, this is important to realize that this region is called as the ohmic region. That is the region which is less than VGS equal to VP. When which is less than VP, then at that VDS less than VP, at that, during that period, this is the ohmic region. What we mean by ohmic region? Ohmic region means that the resistance gets changed in accord, means the voltage is depending upon the resistance, but means or you can say in a simplified manner version, you can say that this region is the ohmic region, and here the junction field, this is the reason where junction field effect transistor is used as a variable resistance, means or you can say it is as a VVR, variable voltage resistance. That means where the VGS, what does it mean, variable voltage resistance? That resistance is being controlled by the voltage, that is VGS. And this is the one application of the junction field effect transistor, that it is used as a variable resistance in this particular region. Here you can see that as you keep on increasing the voltage, your resistance is increasing. It is more and more when you are increasing this voltage. So this junction field effect transistor resistance will be, or which is called as the drain to source resistance, will be given by the formula RD is equal to 1 minus of VGS over VP, where this R0 is the voltage or is the resistance when VGS is equal to 0. This is the resistance when VGS is equal to 0, and these are the VP, you know, that is given by the manufacturer. So by keeping these values, you can always calculate the value at different point of time. So this is the drain to source resistance of the junction field effect transistor. And in the ohmic region, if some question comes in the exam that what is the application of the field effect transistor, junction field effect transistor, then this is the one application. As a voltage amplifier it is used. Also it is used as a variable resistance in the ohmic region. By changing the VGS, the resistance of the junction field effect transistor can be controlled. This is the P channel we have already discussed. The P channel consisting of the P type of the channel, two N type of materials are connected. Gate terminal is reverse bias, that is why this VGS is the positive voltage. Drain terminal is P type of the material, and this is your this is also reverse bias, and that is why it is connected to the positive terminal of the battery. Now, these are the characteristics which are similar to that of your N channel. The only difference here, in the previous case in N channel, that VGS was negative voltage, but here it is positive voltage. And if you apply VGS, which is VDS, which is greater than the VDS maximum value, then some breakdown takes place. And this rise in the current after that voltage is shown in the figure, that shows that this is the breakdown takes place if we are increasing the voltage VDS beyond the VD max. So here this is also written here, that ID increases uncontrollably if you are increasing the VDS more than VD max. These are the symbolic representation. This represents the current which is going into the circuit or coming out of the circuit. So depending upon the direction of the charge carrier flowing in the circuit, this current will be decided. Now, we have discussed about the drain characteristics so far. Now, how do we draw the transfer characteristics? So, in BJT, we know that beta indicates the relation between the input and output current. In JFET, this relationship of the VGS and ID. VGS and ID, because this is a voltage control device. That's why the relation between VGS and ID is given by the Shockley equation, and that equation is nothing but the ID is equal to IDSS 1 minus VGS over VP square. So IDSS is the saturated current which is present, which is the current when your VGS is equal to 0 volt and VDS is equal to VP. At that point of time, the current which we get is the IDSS, and VP is the pinch off voltage. This is the voltage when this voltage is equal to VP, then we get the IDSS. So with the help of this, we can always calculate the, we can draw the transfer characteristics also. So here you can see there are the two ways of doing it. Either you can draw it graphically, or you can do it analytically by using the Shockley equation. So here if you extend this VGS, this is your transfer characteristic, and this is your drain characteristic. So once the drain characteristics has been drawn, if you extend this VDS, VGS is equal to 0, and this is the point where VGS is 0. So at the point of intersection, we mark this point. For VGS, this is -1, and this is also -1. By extending this, we get this point, intersection of these two. Similarly, here the intersection of these two will get these point, and as soon as you apply the VGS is equal to VP, that is, let's say, minus of 4 volt in this case here, then we get this current will be equal to 0. If you connect these points, we get the transfer characteristics. So this is how graphically you can always draw the transfer characteristics with the help of the drain characteristics. But there is another way of doing it, that is the plotting the transfer characteristic by using the Shockley equation. So that Shockley equation will be ID is equal to IDSS 1 minus of VGS by VP. First of all, we have to keep the VGS is equal to 0. As soon as you keep this VGS is equal to 0, your ID will be equal to IDSS. So here you can see that ID will be equal to IDSS when VGS is equal to 0. In the next case, when you keep VGS is equal to VP, so this value will be 0 and your current will be 0. So here you can see then VGS is equal to VP, the current is 0. Now these between 3 points or 4 points or whatever number of points you want to take, you can calculate by solving the value of the VGS in terms of the VP. Means VGS should be taken as VP by 4, VP by 8, VP by 16 intermediate points. So you can always calculate these currents with the help of either the Shockley equation or with the help of the graphical representation. So this is all about your junction field effect transistor. So we have discussed the difference between the in the last two videos. We have discussed about the PN junction, the difference between the BJT and FET, the types of the junction field effect transistor, their working, their construction, and their characteristics. So in the next lecture, we are going to discuss about the depletion MOSFET, that is the junction metal oxide semiconductor field effect transistor, and these are two types, that is depletion type and the enhancement type. So we will be discussing about that in the next coming lecture. Thank you so much. Jai Hind.